can you visit Lima? I don't know if you not Lima, but I believe this opportunity, your presentation to develop connection between your university. No, you can read the college, University College London is the first university in the United Kingdom, but Durham say no, but it's one of the oldest public university in the United Kingdom. In St. Mark University is similar. It's the oldest university of America, of course, in Peru, and could be a good opportunity to think about the public higher education in 19th century, in history, especially in science. Now we have our university has the first woman president.
Okay. Yeah.
Conference in Padova. Padova has 800 history years old. In recently has the first woman president elected. Well, it is in Europe, in America, has a same experience. Women at the top authorities in this moment, in this 21st century.
Okay. Yeah.
Amigos, amigas, quiero resaltar que la profesora Claire Carnal es formada de Newcastle upon Tyne. Está en el norte de esta Universidad de Inglaterra. Luego hace su postdoctorado de Texas en Austin. Con esta universidad ya hemos tenido mayores presentaciones y empieza propiamente en el siglo XXI su experiencia en la docencia universitaria, precisamente en University College London, primero como un investigador y luego como lecturer, en nuestro similar al caso peruano, ¿no? Desde auxiliar hasta principal. Ha sido vicedecana de la Facultad de Ciencias Físicas y Matemáticas, ¿no? Aquí más bien están ambas áreas separadas, pero están unidas. Y ha sido jefa del Departamento de Química el año 2016, hace muy poco, y la Royal Society Chemistry la ha reconocido con premiaciones el año 2000, el año 2019 y recientemente, el año pasado, Tilden Prize por Material Chemistry, que es una distinción muy importante y es un honor tenerla con nosotros ahora a Claire. Well, Claire, in our university, the chemistry faculty, the faculty, the chemistry engineering and
Chemical engineering, yeah.
Usually we are relation with the other faculty, the pharmacy and biochemistry. I suppose in different countries similar, no? In the inorganic, organic chemistry, in the academics, in the different professor and different approach.
Yes.
Well,
Yeah. I mean, yeah.
Andrés, ¿nos estás acompañando? Wait a moment, please. Claire,
Yes.
do you know the America? Do you know Peru?
I don't know Peru. No, not really. I know friends who have been to Peru, but I've never been.
Well, I believe this is an opportunity to develop an experience. San Marcos University is the principal, is the capital of Peru, Lima. At the same time, we have the research place in Amazonia, Peruvian, Highlands, and the Central Coast. And the chemistry and health, organic chemistry, well, the pharmacy, the botany, and the Amazonia, strong connection experience in Peru. Could be very important for your students and research.
Yes. Yeah.
Please, a minute. Wait a moment, please. Andrés.
Sí, profesor.
Claire, Andrés, interpretation. Andrés, ¿puedes presentarte, por favor?
Sí, profesor, parece que hay un eco. Yes. Good morning. My name is Guillermo. I'll be the interpreter for this session, if that's all right with you.
Okay. Yeah, that's fine. So do you want me to just go ahead with the presentation and?
Yes, please go ahead. You can go ahead and I'll interpret.
Okay, let me just share my screen then 1 minute. Oops, sorry. No, I don't mean to do that. Sorry. Hang on a minute, it's not letting me share. No, that's not what I want to do, sorry. Share a window, is it this? That's it. Is that working? I can't see anyone now.
Yes.
Yes, it is. Okay, great. Let me just see if I can go. Okay. So that's working. Okay, good. Okay, so yeah. Okay, thank you. So thank you for the introduction and for inviting me to present today. So I'm going to tell you a little bit about my research that I've been doing University College London, or UCL, over the past few years. We've been looking at scalable routes to functional materials, photocatalytic, TCO and anti-soiling coatings, and I'll explain all of those as I go on. Just before I do, I thought it would be interesting to just give you a little bit of overview on, I can't work out how to change slides, sorry. Yeah. Thought it would be interesting to give you a little bit of an overview of UCL, as you may not be familiar with this. So University College London, as mentioned in the introduction, it was founded in nearly 200 years ago, so 1826, and it's the London's leading multidisciplinary university, and we have over 51,000 students at the university, and we're ranked in the top 10 of universities worldwide. And the chemistry department, which is what I'm head of, is one of the largest chemistry departments and one of the top chemistry departments in the UK. We have over 900 students in the department, mainly made up of undergraduates, but we do have a lot of postgraduate students as well, over 200, which are supported by the academic staff and a number of postdoctoral researchers. And the department covers all the range of chemistry, from chemical biology, computational chemistry, organic chemistry, sustainability, physical chemistry and materials discovery. And it's in the materials area that most of my research is concentrated in. So I mentioned that we're looking at functional coatings, and so I wanted to give you an introduction of how we develop those coatings. The key aim of our research is really, we keep sustainability at the heart of our research, and we're really looking at developing low-cost, scalable routes to functional materials. And to grow the thin films, we use a process known as chemical vapor deposition, or it's often called CVD. And the reason for using that process is that it's a great process for depositing a wide range of different functional thin films, and you can get deposit over large areas, and we tend to deposit on glass substrates, partly because of the applications we're interested in, but also because we have a collaboration with a company known as Pilkington NSG, who are the world leaders in functional thin films for windows coatings. So if I could explain the CVD process to you. So I do have a little video if I can get it to work. So essentially what you have to do is heat the precursors up into the gas phase, and you get mass transport of the reactants in the gas phase, where the reactions can occur between the chemicals. You then get diffusion of precursors onto your substrate, which is typically heated up. You get absorption of the precursors onto the substrate, followed by surface diffusion, surface reactions to hopefully form the thin film that you want to form, followed by desorption of any byproducts. And those byproducts can then be removed. Now, traditional CVD takes place either as low pressure CVD, so you would have a vacuum pump, and so I'm just going to get a laser pointer. So you'd have a pump and your byproducts could be pumped away, or it's often done under atmospheric pressure, and so you would have a carrier gas such as nitrogen. And it's the atmospheric pressure CVD, or often known as APCVD, that's used commercially by Pilkingtons to deposit the functional coatings on glass. So with APCVD, the byproducts would be taken away by the carrier gas. Now, it's a really excellent process, but it does have drawbacks, because the precursors have to be volatile enough to get into the gas phase for then the reactions to occur and the thin film to grow. And that obviously limits the number of chemicals that can be used, and often chemicals that are volatile enough tend to be quite pyrophoric or corrosive or toxic. So we changed this slightly and we moved to a solution-based CVD, which is known as aerosol-assisted chemical vapor deposition, or AACVD. And in this case, you take your precursor or precursors and dissolve it in solution. Then you create an aerosol using, there's different ways which I'll talk about in a moment, but you create an aerosol. The aerosol is then pushed into the reactor using a carrier gas, such as nitrogen. In the reactor, you have a carbon block that heats up your substrate. So that would be our glass substrate. And it depends what temperature relates to which film that you're trying to deposit. So it could be anything from 150 degrees up to 550, although the industrial process takes place at higher temperature, but that's above the softening point of glass. So we tend to stay below that at about 550. We have a top plate present, and that just allows the aerosol to have laminar flow through the reactor. And of course, once your aerosols come into this heated area, then the solvent evaporates away and your chemicals are then, your precursors are there ready to decompose on the heated substrate and hopefully grow your thin film. So the other advantages of the AACVD process, as well as overcoming the volatility of the precursors, is that it can lead to the formation of very highly textured surfaces. And this just shows you an SEM of one coating that we have produced using AACVD. And by forming highly textured surfaces, you can then tune it towards the functional property that you're interested in. It also is compatible with scaling up to the industrial online APCVD process, but I'll come back to that later on in my talk. So all the films I'm talking about today have largely been deposited using AACVD. So if I just give you a little bit more information about AACVD, because I mentioned about the textured morphology that you can form, but that's very dependent on the way that the aerosols are formed, so the aerosol droplet size, but also the solvent that's used. And there's a couple of different ways that you can form the aerosol droplets. This diagram is quite nice because it compares what sort of the morphology that you get from the different techniques. So there's APCVD here, so that's where you just put the precursors into the gas phase, and you tend to get quite featureless morphology forming. Then there's one I've called UAACVD. So this is where we use an ultrasonic humidifier to create the aerosol of our precursor solution. Now this actually forms quite large aerosol droplets, and so when that's used in AACVD, you get this quite textured morphology as shown here. If you change the way you create the aerosol to something known as a collision atomizer, which produces the aerosol droplets under higher pressure, you tend to form much smaller droplet sizes, and then you can end up with even greater textured morphology. So that can be quite important depending on your property. Most of the ones we do uses the ultrasonic, just it's much easier to set up and use for the students and so on, but we have done quite a lot with collision as well. And this just gives you an example of the Pilkington float glass process. So as I mentioned, they tend to heat up to very high temperatures above 600 degrees, and it's in the float bath in this area here that the coating takes place using APCVD. So if we wanted to incorporate our AACVD, it would be in this area that you would have to incorporate the film growth into. So let's have a look at some of the applications that we've been interested in. So we're interested in a range of different applications, things like optoelectronic devices, solar cells, photovoltaics, low emissivity window coatings, and so on. And I'll mention some of those as I go through my talk. I've put on a quick schematic of a typical device, and you can see the different layers that's within the device shown here. So you have this layer, which is the transparent conducting oxide, which is known as a TCO. And then all the different layers as shown here. We have deposited most of these layers, but obviously because time's short, I'm just going to highlight a few of them today. So TCOs have been of much interest because these have this this sort of joint property of being very highly transparent, but also high electrical conductivity simultaneously. So you're looking at transparency above 80% and resistivity less than 10⁻⁴ ohms per centimetre. Now, the commercial TCO is based on ITO, which is indium tin oxide, which is really excellent, but there have been considerable concerns over the supply of indium, and so there's a lot of interest in finding alternative TCOs. Now, often when you're looking at things such as solar modules, one problem is they're often outside trying to get solar energy, and what can happen is that you can get soiling on the glass top surface. And so we've been very interested in developing coatings for that, which are known as anti-soiling coatings. And this is because due to the soiling, you can get optical transmission losses that occur at that glass surface due to reflection and soiling. The soiling comes about due to things like dust or sand and so on. So I'll talk to you a bit about some of the anti-soiling coatings we've developed. And then I'll introduce a couple of other areas we've been interested in, which is photoanodes for photoelectrochemical PEC cells, so that's water splitting, and also photocatalysts, and this is where we've been looking at sunlight activated coatings for applications in self-cleaning windows. So if I start with the top layer, and this is anti-soiling coatings. So this just shows you a photo of some solar panels. I think it's out in a field in the UK. And over time, you can see that dust has accumulated. And as I mentioned, that can cause optical losses due to on the solar modules. And of course, then that causes reductions in power output and then can increase costs. And there's obviously a drive towards more and more energy being derived from solar. So we really need to find ways to overcome these issues. Now, the way it's currently solved at the moment is that the solar modules are cleaned. There's an anti-reflective coating of silica on the top surface, so they're applied to about 90% of these modules. Now, silica, to get it anti-reflective, it has to be quite porous silica. They're hydrophilic, and the problem is because it's porous, when you go through the action of cleaning, and the cleaning of the utilities is largely done using very large sun brushes that are on tractors, you can see that it ends up causing damage to the porous silica. And also the silica being hydrophilic increases the adhesion of the soiling to the surface. So attention's been changed from hydrophilic coatings to hydrophobic. And this shows you an example of some solar modules where one panel, which is this one in black, has been coated with a hydrophobic coating. It's then snowed, and you can see that on all the other panels, snow's accumulated onto the panel, but on this one where it's hydrophobic, it's completely clear. So we're very interested in looking at developing hydrophobic coatings that could be used for anti-soiling coatings in this application, or indeed other applications as well. So as well as hydrophobic, we've also looked at super hydrophobic. So if I could just introduce that to you. So obviously all hydrophobic and hydrophilic interactions really arise due to the surface chemistry of the material. If you're looking to go from hydrophobic to super hydrophobic, what you have to have is quite a rough nano or microstructure. And this gives you an example of a super hydrophobic film we deposited. I'll talk about those in a moment. And this is just a side-on SEM. You can see how rough the morphology is. But they also need to have a very low surface energy. And that's because when you put water onto the super hydrophobic surface, rather than the water spreading out, it actually forms, due to the high water repellence, it forms these spherical water droplets. And because of the low surface energy as well, they don't stick to the surface, and so as they roll they can act as sort of self-cleaning or help to clean. Now, to define if something's a super hydrophobic surface, we measure the water contact angle, and it's showing you here how we measure what the water contact angle is. And if it's hydrophobic, it's above 90 degrees, and if it's super hydrophobic, it's above 150 degrees. So where we started with this was a number of years ago, looking at titanium dioxide. We took some dual scale nanoparticles, so some very small nanoparticles and some larger ones. We mixed those up in ethanol, and then we added this perfluoroalkyl silane, which that's there to help provide the low energy surface that's required. In the video that was running, I think I have to turn my laser pointer off to get the videos to run. What we've done here is taken that paint and put it onto actually just blue tissue that you get in a lot of laboratories, let it dry, and you can see now the water doesn't absorb at all into the tissue. It's completely just rolling across the surface. Now, because it's like a paint, we're able to take different coating methods, and that's shown in the diagram shown here. So you can either spray them onto hard surfaces, such as glass and steel, or dip coat onto soft surfaces like cotton and paper. I'm just going to set these videos going while I talk. And you can see on the left side, that is the uncoated surface where the water droplet spreads out. On the right side is this coated substrate where the droplet is spherical and is repelled. And you can see in the top video that what happens is you get lots of bouncing of the water droplets due to the very hydrophobic nature of the surface. And also in the bottom video, we've put some dirt onto the surface. As the water droplet rolls, it picks up that dirt, and as it rolls, it takes the dirt away. And you can see it leaves a very pristine surface behind. So that would be a way of trying to help reduce any soiling on surfaces, whether that's in photovoltaics or in other applications such as in car wheel hubs and that sort of thing, by this rolling action. Now, obviously, if we wanted it in a solar module, we'd have to have a transparent coating, and you can see from the top video that these are white, like a white paint, so it'd be very good on the walls in your house or in your office, but obviously not so good for photovoltaics and so on. So we had a look at seeing, just see if I can move on, could we use AACVD to try and grow thinner films and get them more transparent? And there's obviously sometimes a trade-off between the thickness of the coating and how rough they are and how hydrophobic. But we moved from using titanium dioxide to using silica because we thought that might enhance the transparency. But we did a similar mixture where we had the silica nanoparticles. Again, we used different scales, so very small and some larger ones. Then we added in either a fluorinated silane, or to move away from fluorine, because obviously that has some environmental concerns, we also have looked at using a mixture of stearic acid and palmitic acid, because these fatty acids also provide the sort of low surface energy that's required. But for the AACVD, one of the problems you get is that when you try and deposit a super hydrophobic coating or a hydrophobic, it's not very adherent to the glass substrate. And what often happens is, I mentioned about the AACVD that you have your glass substrate at the bottom and your top plate. So normally your film grows on the glass substrate. But what happens with when you're using large polymers or large particles, that you get thermophoretic forces, and this ends up causing the super hydrophobic film to deposit on the top plate rather than on the bottom, which doesn't really matter apart from it's the wrong way up, and you would have to think about things if we were incorporating it into the industrial process. But to overcome some of the adherence problems, what we did was to add in polydimethyl siloxane, or Sargard, which are these shown here. And that just acts to help as a sort of glue, to help it adhere better to the glass surface. And you can see this is the SEM of our resulting films, and you can see a nice rough morphology. And we looked at the deposition under different temperatures, so between 250 and 450, and between 300 and 400, we were getting super hydrophobic water contact angles. So that was good, and our adherence was quite good. Sorry, the solvent we used was ethyl acetate. So the adherence was good, but it still needed improvement, and the transparency was quite good, but again, not quite as high as we'd want, as it needs to be over 80%. So we looked at some alternative methods for producing this, and one was to think about doing shorter depositions. So an AA-CVD experiment typically takes between 20 and 60 minutes. And what we thought was if we could go down and reduce the deposition time, we could then potentially get much thinner films. But if we just do it in one pot like normal, then potentially we wouldn't actually get the hydrophobicity that we wanted. So instead we built it up layer by layer. And so we put in a bottom layer to begin with, just a quick 5-minute deposition using this methoxysilane shown here, which kind of acts as a sticky layer. And then our middle layer, we added in this tetraethyl orthosilicate. And what happens with that precursor is during CVD, it forms silica nanoparticles. So that, again, that was just a quick 5 minutes deposition. And then we did the final layer, which is where we added our fluorosilane to give us the low surface energy. And you can see this just showing the film from the side. You can see the water droplets forming a very high water contact angle of 165. And this over here is where we've typed super hydrophobic onto a piece of paper, and our coated glass substrate sitting on top. So you can see that the transparency is very, very good. The one drawback of this is that we're still using the fluorinated silane, so we do need to look into that again in the future and see if we can create the same good adhered surfaces, but not using fluorinated species. So the other way we've thought about it is instead to think about pre-treatment. So there's a couple of ways we've considered this, and this is just to try and help with the adherence of our super hydrophobic material on the glass substrate. So first of all, sometimes we do a mixture of both. So using air plasma, you can enhance the number of OH groups on your glass surface. We've also looked at adding an initial layer, just brushing it on and then heating at 150 for 40 minutes. And this was of this epoxy silane shown here, which again can just sort of act as a bit like a sort of glue. And then we did our AA-CVD. This time we just used polydimethyl siloxane with our silica nanoparticles. So we got no fluorine present there, and that deposited on the top layer. You can see the SEM over here, and they were really good films in terms of their adherence. They're not quite as transparent as we like, but they're getting, the transparency is not too bad. So I think we can improve this, and they have a very high water contact angle. And we were able to show that by having this intermediate layer of the epoxy silane really helps with the robustness of the films. And this is just one example where we submerged them into different solvents. This one's diethyl ether. The top line is where we have the epoxy silane layer underneath our super hydrophobic film, and you can see over 5 hours there's not much change in the water contact angle, so they're still super hydrophobic. However, without the epoxy silane layer, you can see that dropping off over from 0 to 5 hours, and that's because it's just not very well adhered to the substrate surface. So in the solvent, some of it's getting lost during the submersion. Now you can do depositions of hydrophobic species, and instead of using polymers, you can use alkoxides and so on, or metal oxides. And so we had a look at this. Well, we'd done this a number of years ago, which was where we made this titanium dioxide, tin dioxide composite film. So you can take titanium isopropoxide in ethyl acetate on its own, and you deposit TiO2, and you can see the water contact angle was 100 degrees for that, and that's the morphology. You can take butyl tin trichloride, also in ethyl acetate, and form tin dioxide, similar, slightly higher hydrophobic contact angle. Or if we take this as a mixture in our AACVD bubbler, you can then add in ethyl acetate, do the AACVD at 450 degrees, you form a TiO2 SNO2 composite film, and you can see you get this very, very unusual morphology. We originally looked at this for photocatalytic applications, and it really did enhance the photocatalysis, we think, because of such a increased surface area. But also looking at this, we thought it could work very well for an application known as SLIPS, which is slippery liquid infused porous surfaces. Now they're of interest because they're not super hydrophobic, instead they're slippery. So rather than just being repellent to water, because they're slippery, then they can also repel other liquids like oils and so on. But typically what you have to do is add a lubricant on top of your surface. And so that's what we did in the next step. So we made our AACVD film of our TiO2 SNO2, and then we spin coated a lubricant on top. And then what we did was look at them for a range of applications, such as anti-icing, anti-fogging. So essentially we just looked at how long the water droplet took to freeze, just using this little homemade icing chamber shown here. These are just the AFMs of the films, showing you how textured the morphology is. So did it work? Well, we did quite a few different experiments. What we did was the same reaction, so the titanium isopropoxide and the butyl tin trichloride, but we varied the solvent that we used for the AACVD reaction. And you can see we had 6 different variations. Then we measured how long the water droplet took to form ice, and we compared it to the blank glass substrate. We compared it to the lubricant just on the glass, and we compared it to the plain AACVD film that we deposited with no lubricant on top. And you can see for the first 3, it typically took between 3 and 5 minutes for the water droplet to freeze. And then we managed to increase it a little bit. And then for sample 6, where we used a mixture of ethyl acetate and dichloromethane, we've now increased the time up to 30 minutes for the water droplet to freeze. So that's quite a big change. Obviously, we'd like to enhance that even for a longer time, but that was a big step change from 3 minutes up to 30 minutes. We did look at also some frosting and fogging tests, which I'm not going to go into in detail, but essentially that same sample was shown to be the best one, and did show some acting as an anti-fogging. And a lot of this is down to the fact that you're limiting the areas for nucleation to occur for the ice to form. Okay, I hope that's given you an overview of some of the hydrophobic films. What I'm going to do now is move on to another layer in the device, and that's the TCO layer that I mentioned in my introduction. So I mentioned before that ITO is the typical commercial transparent conducting oxide, and we have made this ourselves. You can make it via AACVD by taking indium trichloride with butyl tin trichloride in methanol, and this shows you the side-on SEM, and we formed very nice ITO films. We were interested, obviously I mentioned about moving away from indium, but another way you could think about it is, can we just reduce the amount of indium that's needed? It's quite difficult to find other materials that have such good functional properties as ITO. So we were interested in doping it with molybdenum, because molybdenum would then be in often oxidation state 6 or possibly 4, and so it would have extra electron carriers to enhance the conductivity. So what we did was take indium trichloride and methanol, and then add in dopant amounts of this ammonium molybdate, again in methanol, and we created a range of different molybdenum doped indium oxides. And we had a look at that and compared it to literature. And you can see this is a photo of our film, so you can see they're nice and transparent. So this is the ITO and this is the IMO, so the molybdenum doped indium oxide. I'm showing the IMO in red and ours are the circles, and the ITO in blue and ours is the circles, and we're comparing it to literature by the stars. So you can see for the IMO you get lower resistivities than for the ITO, so that's good, lower resistivity, so better conductivity. And also importantly, you actually get higher mobility as shown for IMO versus the ITO. And we did a lot of computational studies. I'm not a computational chemist, though, but essentially we were able to show from the computational studies that this related to the molybdenum 4D state sitting quite high up in the conduction band minimum. And so essentially what you get with the molybdenum doped species is you get a higher mobility and so therefore a higher conductivity with the same carrier concentration. And so we were able to show you could use much thinner films of IMO to get the same properties that you need for the ITO. But we wanted to move away from using indium, and so we've done a lot of work with other metal oxides. So we've shown a range of different doped tin oxides as really good TCOs, and we've also looked at a range of different zinc oxide coatings. And I just thought I'd highlight one to you today, which is looking at a gallium doped zinc oxide coating. So here we made a novel precursor. So zinc oxide is often deposited using diethyl zinc, which is pyrophoric. Excuse me, sorry. But very effective, but it's pyrophoric. Or you can use zinc acac, or you can use zinc acetate. But the zinc acac and the zinc acetate don't give you as good resistivities. So if you recall, I said you need resistivities about 10 to the minus 4 or lower. And you would typically get resistivities of about 10 to the minus 2 using those precursors. So instead we designed this precursor, which is ethyl zinc isopropoxide, and it forms this tetramer shown here. We then dissolve this in propanol, and then we use this gallium acac to add in dopant amounts of gallium to form our gallium doped zinc oxide. The SEM shown here, this is the plain zinc oxide, and then this is as we're increasing the amount of gallium dopant. And the best one was this one shown here, which had 3.8 atomic percent gallium doped into it. And it had a really excellent resistivity of 10 to the minus 4. The other thing that was really interesting when we looked at the transmittance reflectance properties is that it actually showed really good properties for low emissivity or low E window coatings. Now these are important coatings because they improve the insulating properties of windows. To get a low E window coating, the properties that you need is that you have to have high reflectance in the mid or far infrared, and you have to have high transmittance in the visible. And here I'm comparing our GZO, so our gallium doped zinc oxide is in green, and I'm comparing this to commercial, some commercial low E coatings, which are known as things like Tech 8 and Tech 15. They're based on fluorine doped tin oxide. So you can see ours is performing comparably or even better than the commercial coatings. Now it is interesting looking at the precursors themselves. So this over here was the precursor I just talked to you about, the ethyl zinc isopropoxide. I mentioned that you can use zinc acac as well, and we also compared it to ethyl zinc methoxide. Now these two are quite interesting because you can either make the precursor as shown here, isolate it, dissolve it into a solvent, and then do the aerosol assisted CVD as I've talked to you through before. Or what you can do is do a 2-bubbler setup. So you could have your diethyl zinc dissolved in probably toluene in one bubbler, and then your alcohol, so your methanol or your isopropanol in the second bubbler, and then they enter into the AACVD, and as they react, they presumably form these types of species before forming the zinc oxide. And it's interesting when you look at the XRD because you get very different results depending on the precursor. So when you use zinc acac, you don't get much, it's not very crystalline at low temperatures. And then you can see that you're getting preferred orientation. These crystal planes shown here relate to the crystal planes in zinc oxide, starting from this side going across. And so you get preferred orientation in the 002 plane shown here. Now, these two here are when you take diethyl zinc with methanol, so either with hexane as the solvent or with toluene. And then these are where you're using diethyl zinc with isopropanol, isopropanol, either in hexane or toluene. So you see you're getting very different XRDs that are forming. So for when you're using the methanol, you can see you're not getting that preferred orientation in the 002 plane. However, you are when you're using the ethyl zinc isopropanol. And what this relates to is that you typically get these this type of XRD for zinc oxide if you have a oxygen-rich environment around the zinc, whereas if it's oxygen poor, you tend to get this type of XRD formed. And so what we believe is happening is if you have the isopropanol, you form this complex in solution and it goes on to form this zinc oxide. With the methoxide, we don't believe it's forming this in solution, and so it's acting, just reacting diethyl zinc with methanol, and so you get a different XRD coming out. Going back to the original device that I put up, the other layer I was just going to mention was the perovskite layer. So there's been a lot of work at looking at the solar absorber layer, and lots of people have used lead-based materials such as methyl ammonium lead iodide, which we've done a little bit of, but obviously it'd be good to move away from lead for sustainability reasons. We've been interested in bismuth halide-based hybrid materials. So here we use this complex shown here. So we made this iodobismuthate compound, and we chose to use this large cation. It's an ammonium cation that's quite hydrophobic. This is the crystal structure, and you can see you form these beautiful crystals. And you can then use this in AACVD, and you deposit a film, which is shown here, which on annealing then looks like this orange film shown here. We looked at the band alignment and decided this is our bismuth iodide, and we decided to deposit it on plain glass, also on TiO2, which had been deposited on glass, and on fluorine doped tin oxide. Now, as deposited, you still see peaks due to the solvent. We have to use DMF as the solvent, and so you have to anneal it to get rid of the DMF. So you either can heat that up in vacuum at 120 or under nitrogen at 150, and then you get a good match to the standard pattern. We did try and make a device, but it didn't work very well. But the one thing that was very positive is that it actually shows very good moisture resistance and good ambient stability, which is largely due to the very hydrophobic nature of the cation. So it would be worth pursuing in more detail that material. While sticking on bismuth materials, we've also been very interested in these oxy halides. The reason behind that is because when you look at their structure, this is the sort of layered structure that they have. So you have layers of your sort of oxo-bismuth cation with your halide ions sandwiched in between. And that leads to internal electrical charges, which is thought to help reduce recombination between the electrons and the holes. So what's happening when you're interested in these as, for example, photocatalysts, you're obviously irradiating with UV or visible light, and your electron then is promoted from the valence band to the electron band, conduction band, sorry. And so you're forming electrons and holes. These then take place in the oxidation and reduction reactions. But what can often happen is that the electrons and holes can recombine either within the bulk or at the surface, and then that would limit your or completely stop your photocatalysis. So often what people are doing are trying to find ways to prevent that recombination, and ways that you can do that is obviously by tuning the band gap, and that can be from doping or forming heterojunctions. So what we were interested in was to look at the bismuth oxybromide, but doping it with iodine, and that's because it's on the next slide actually. When you look at the band gap, the bismuth oxychloride, the band gap's too large, so it doesn't really show any photocatalytic activity. If you look at the bismuth oxybromide, that shows good photocatalytic activity, but it's quite limited in the visible region. And if you look at the bismuth oxybromide, that oxyiodide, sorry, you can end up getting electron hole recombination. So if we could get somewhere between the two of these, that could be a very effective photocatalyst. So when we've made it, we then test the photocatalysis, and we use something known as an intelligent ink. We spray that onto the surface, and then we photoexcite using UV and visible light. You start with this compound, which is known as risazorin, which is blue, and the photo-generated electrons reduce the risazorin down to this pink intermediate, and then it can go all the way to this colourless intermediate. And the change in colour of the ink is monitored using digital images, and the faster the dye degrades, the more photocatalytically active the film is. So did it work? Well, here's our bismuth oxybromide, and then we've added in dopant amounts of iodine. You can see the XRD, and that's the plain bismuth oxy iodide at the top. When you look at the XRD, you can see the peak shifting as we're doping with iodine. And then this is the SEM and the AFM, so you can see, and that's the sort of morphology you'd expect for these oxyhalides. This picture shows you the digital images. So this is an uncoated substrate, and as expected, you expect to see no change. This is one of our films, and you can see the change as it's progressing, as the photocatalysis is working. So looking at the rates of that risazorin conversion, we're comparing the plain bismuth oxybromide with our iodine doped films. And you can see the best one here under UV is the bismuth oxybromide, which is probably expected, and then it gradually drops off, with the exception of this one, which seems a little bit different. This one I've labelled 1I4BB. This has 2.4 atomic percent iodine doped into the bismuth oxybromide. And what we found is when we looked at it, did the same photocatalysis but under visible light, what we found is we see the lowest activity from the bismuth oxybromide. That increases until the best one is that one with 2.7% iodine doped into the bismuth oxybromide. And basically what we're seeing is an uplift of the valence band edge. It's narrowing the band gap of your bismuth oxybromide, and that's the best size that you're getting to get the most active photocatalyst. We also were interested in heterojunctions, as I've mentioned previously, about trying to get the best heterojunction that you can form. So here is so here's the bismuth oxybromide that I mentioned before. We looked at the band gaps of different materials, so the zinc oxide and the TiO2. We decided the zinc oxide had a good alignment, and heterojunctions can be good because when you irradiate with UV or visible light, and you get the electrons promoted from the valence band to the conduction band, rather than recombining, they can then transition to the other semiconductor in the heterojunction. So we looked at forming these heterojunctions, and we did it in two ways. One was where we had bismuth oxybromide as the lower layer and then zinc oxide on top. And then the other way around, we put bismuth oxybromide, sorry, it's not the bromide, it's the iodide, apologies. Bismuth oxy iodide on the bottom with zinc oxide, or zinc oxide with bismuth oxyiodide on top. And these are the SEMs. So this is the plain zinc oxide, and this is the bismuth oxyiodide. When you have, this is where you have zinc oxide on the bottom with your bismuth oxyiodide on top, and so it adopts a similar morphology to the bismuth oxyiodide. And then the other way around, when you have the bismuth oxyiodide on the bottom, zinc oxide on the top, you can see it adopts a very similar morphology to the zinc oxide. Now, if the bismuth oxybromide's on the top, that doesn't work very well. And we think it's largely due to the formation of bismuth hydroxides, and so which is insulating, so it's not very active. However, if we have zinc oxide on the bottom and the oxyiodide on the top, it's much more efficient. So what we're interested in these is as the photoanode for use in the photoelectrochemical devices. The photoanode, this takes part in the formation of the oxygen. So, and then at the cathode, you have the formation of hydrogen in the water splitting. And we had a look at, this is the instant photon current efficiency. And we looked at the plain bismuth oxyiodide, which is shown in yellow. We looked at the plain zinc oxide, which is shown in green. We then added those two up to just check it wasn't just giving us the sum of the two. And then this is our heterojunction. And what we see is that it shows significantly enhanced photoelectrochemical efficiency. And what we're seeing is increased visible light activity of the heterojunction. And this is due to, we believe, we're getting enhanced charge carrier separation by having the heterojunction present. Okay, just the last thing I wanted to mention to you was about this whole issue with scaling AACVD. Just as a last slide for you. So essentially what I mentioned before is that the AACVD reaction can take between 20 and 60 minutes. However, when I mentioned to you about the industrial process, when you're growing your coating within the industrial process, and it takes place in the float bath, this the coatings here, and that could be, I don't know, a TiO2 coating for self-cleaning applications. That deposition is typically done in less than 60 seconds because actually the glass is continuously moving. So obviously at the moment the AACVD isn't compatible with that because you can't really stop it for 20 to 60 minutes to do the coating. So lab scale AACVD reactions really give quite slow growth rates. So the growth rates are about 10 nanometers per minute. So that's using the ultrasonic form of forming the aerosols. So we did quite a lot of studies. We used fluorine doped tin oxide because it's we just wanted to grow an easy film because we just wanted to understand the growth rates rather than changing the properties. And you can grow that using butyl tin trichloride with dopant amounts of ammonium fluoride and methanol. We had the temperature at 550. And by changing to that collision atomizer that I mentioned right at the start, using much smaller aerosol droplets, we were able to reduce the deposition from sort of half an hour down to 5 minutes and getting growth rates of 100 nanometers. That's still not fast enough. So we have also looked at alternative nozzles where the aerosol is generated much more quickly. And then we have been able to achieve much faster growth rates of 2 micrometers per minute. So we're getting closer. We can deposit the film in less than in around a minute. So we are still quite hopeful that this could be compatible with the industrial process. And this just shows you the film. It's our FTO film deposited on glass. We're kind of looking through our film out of the window to the building opposite our building. So very nice transparent film, and it did have the resistivity that's needed. Okay, well, I hope I've given you a nice flavour of what the sort of research taken on in my group. I've talked a lot about the AACVD routes that we've developed to a range of different materials, the photocatalytic, superhydrophobic, TCO and so on, and that we have managed to achieve functional properties that are comparable to or better than commercial standards. The reason for doing a lot of this is to link out into applications, whether that's self-cleaning or photovoltaic and so on. We've overcome some of the issues that you get with superhydrophobic materials, so some of the robustness, but there's still obviously quite a lot of way work to do to try and get them completely robust and completely transparent. And we've gone some way to enhancing the growth rates of the AACVD and getting much faster than current lab-based methodologies, AACVD methodologies. Okay, what just remains for me to acknowledge people who've actually done the work. So these are my current students. These photos are taken last year. I need to get an up-to-date photo just outside of our departments. Some of the work I talked about was some of my recent students who have graduated now. I'd also like to thank my postdocs and lab managers, and also my collaborators as well as funding as well from EPSRC and Pilkington's. And also thank you to you for your attention.
Thank you. Thank you. Well, but the chat, I share some papers, some improvement on your laboratory Carmel and Parking.
Okay, thank you.
And Parking Research Group. I would like to ask precision from our institution to your dean, the practical side, Professor Parking. Well, Claire, in this moment, we are suffer the consequence of the COVID-19.
Yes.
So this is part the CVD is very important to think into the next global pandemic. No? For example, the keyboards, the smartphones in general, no?
Yes, absolutely, and we have done work before. I didn't talk about it today, but you can use it very much for antimicrobial surfaces. And some of the work we're just about to start with Pilkington's is looking at some of the coatings for sort of antiviral and so on as well. And some of the super hydrophobic work we linked with a company who actually puts the floors down in hospitals, you know, when you go down the long corridors. Again, that was for super hydrophobic to help with the cleaning, but they were very keen that, you know, now a lot of places, instead of using tiles, use panels, that you could have antiviral or antimicrobial coatings on those panels to maybe try and help with infections.
Well, the second aspect is about the clean energy. Mm-hmm. So there are different climates and weather. You need tropical, no, for the cellular solar. So in this area, with the renewable energy
mm-hmm.
and the materials, in your experience, well, will be the key challenge in this 21st century to improve.
Yeah, for the solar modules, I think the sort of AACVD that we do would be quite challenging for the solar absorber layers, because I think some of the difficulties is the sort of morphology we get, then can end up not being very good for the functional properties. But I think where it could be very good is in the anti-soiling coating, particularly because you're looking at needing to coat large areas, particularly if you're looking at, say, some of the solar panels that are, you know, on people's roofs or out in the fields and so on, or in the desert. But there are other CVD techniques that might work better, or film deposition for some of the other layers. But I think it could be very important. I mean, I think you know, certainly in the UK, there's a push for more and more solar energy, and I think that's true across much of the world, maybe not everywhere. But, so I think it's something somewhere that materials chemists and other areas as well, physicists and so on, can really contribute towards.
Claire,
Mhm.
20th century, big difference between the global south and global north. 20th century, but now 21st century, we can see expansion the some country in the global south, Indonesia, Brazil, and the other. So, what is your experience with this projection, the material chemistry in global south? What is in your laboratory, your students from the global south?
I can't quite understand what you're saying. Global?
A student in your department, in your laboratory from South America, Africa, East Asia.
So you're asking me if we have students from those countries. Majority, a lot of international students that come to UCL are largely from China, but we do get other students from a range of different countries, I think over 40 countries, but they tend to be small numbers. We've certainly had students recently and postdocs as well from Brazil, and you know, a few other countries like that, but it does tend to be quite small numbers.
Well, in this moment, we can see Europe has a challenge, the war, Ukrainian and Russian war, and this situation has impacted the budget to the science, and projection to connect the science with security.
Mm-hmm.
In your area, you have this impact?
Yes, I mean, we had a bit of impact due to Europe, because obviously the UK went through Brexit and left Europe. Well, left European Union. We haven't left Europe, of course. And that did cause some difficulties because, of course, students now from Europe are also international students. Whereas when we were part of the EU, they were treated the same as UK students. And so that causes some difficulties because those students now have to pay international fees rather than home fees. So, you know, it certainly makes it more challenging for them or for us finding, you know, sufficient funding for the international fees. I think in terms of the question you asked to do with the wars and so on, I think in general funding has been challenging. Certainly our government has decided certain areas it really wants to push money into, such as AI, but otherwise it's quite a challenge competing for funding. You know, I've been quite lucky to keep my research group going, largely because I link with industry, and so they've been very good at supporting PhD students, but it's definitely a challenge. And there's been difficulties in the UK with chemistry departments because it's a very expensive subject. And so some smaller departments have either had to merge with other departments or have ended up being closed. So again, we're quite fortunate at UCL that we're a big department. I think that gives us some stability and attracts some funding as well.
Well, Claire, for the society is a key aspect, connection between the women and science, women and science and research.
Mhm.
In your experience, in your university, your city, how is this transition, no, this 20th century, 21st century, women and science?
Yeah, so I mean, women in science. I mean, I'm lucky being at UCL because they've been very supportive of women in science, and you know, I've been head of my department for 9 years now, so I've been able to lead a lot in that area, and we've won awards and so on for trying to develop that. I think if I talk to colleagues who are a little bit older than me, they certainly had a lot of challenges when they first started out, particularly around things if they took maternity leave and how that affected their career. We've gone a long way now in trying to help support women in science, in either helping them with their returning from maternity. So in my department, for example, I try and ensure that they get a sabbatical when they return from maternity leave, so that they don't return and have to cope with their teaching and their research and everything, and getting used to being back at work and so on. So they get a 6-month sabbatical, which helps them to get their research going before they then start their teaching and so on. So there's been a lot of improvements, and I do think what really helps is how supportive whoever the person in charge is, because I've been able to do a lot of that in my department, but it really depends on who's there leading it. But the Royal Society of Chemistry and the Royal Society in the UK have also pushed forward with a lot of, they call it breaking the barriers and things like that, for women in science. So I think that's improved an awful lot. Have you found that in your country as well?
In my country, middle 20th century, start the migration, the rural to urban, the increase the cities.
Mhm.
Lima, in the middle century, half million people. In the last 20th century, 50 years, Lima has 7 millions, 8 million. In
Wow.
50 years, more than
That's a lot.
10 times
Yeah.
increase.
Yeah.
At the same time, the rural society has a patriarchal approach. The city in South America continuing this traditional approach. In the last 20th century, very important, the Europe experience, American experience, because the people has the graduate, postgraduate study in Europe and North America.
Yeah.
The ruling class in general continued Brussels approach, Washington approach. So the women need more attention in the economy, in public society, and university. Yes, of course.
Yeah.
In the last 20th century, it's a different situation in the middle 20th century.
Right.
But we have several challenges, especially in science and engineering. But I'm historian. I developed a research about the women health science before the Second World War. In
Right.
Lima, in Peru, we can see important number the women's in pharmacy. no? Could be the
Yeah.
traditional connection, women and health, when open the university in the 20th century for the women. In 30, 40, we can find several women with pharmacy and has some chemistry no course in the question, special no, in health. But the problem, very difficult for the women in the middle 20th century to develop in the professional area.
Right, okay.
But there are a long tradition, this connection, women and health, and women and pharmacy.
Yes, yeah. I think that's true with us, actually. We also see larger women moving towards, say, pharmacy. There's had to be a lot of work done to try and develop more women going into, you know, other sciences like physics and so on, but it's still quite low numbers. We're actually quite good in my department, so the number of percentage male to female at undergraduate is about 50-50. It does reduce slightly when you go up to PhD. It's more like 60% male, 40% female. But compared to, you know, other trends, that's quite good. Although obviously we'd like to improve it further. My group, yeah.
I would like to share the experience. This small seminar has a professor from Malaga University. In Malaga University, Andalusia, Spain,
Yes.
in law department, in law faculty, majority students are women.
Oh, right. Okay. That's good.
Women with power.
Yeah, women with power, yeah. Yeah, I mean, when I took over as head, we didn't have many female academics, and we have enhanced that now, but it's probably still only about, I don't know, a third of the department.
Claro.
Yes.
Director, for example, Politécnico Madrid, chair. It's very difficult to find a student from master in telecommunications. So
for what? Sorry,
yeah,
masters. Did you say?
We have in some university, some director share is difficult in engineering, master engineering, the students, because the student decide to private, professional, and no postgraduate. But
Right.
in your area, it's similar.
So, well, our degree, we have two different degrees. So we have an undergraduate degree, which is known as a BSc, and then we have an undergraduate degree, which is an MSci, so Master of Science, but it's all done in 4 years. And then we have a standalone one degree, which is an MSc, so Master of Science. So what we find is a lot of our overseas students prefer to do the 3-year BSc and graduate with a bachelor's and no master's. But then we do get other students wanting to come to us to just do the 1-year BSc. And we only get those that stay on to do the 4-year undergraduate who really think they want to stay in chemistry, whether that's a PhD or industry. Otherwise, they do tend to leave after 3 years and just graduate with a bachelor's. I think that's probably has changed over the years. So I think a number of years ago, I think everyone would tend to do the 4 years. But I think now with, you know, how expensive everything is and wanting to get a job and earn money, unless they really want to do the chemistry, they tend to do the 3-year degree.
Yes.
Yeah.
Our country in this 21st century probably in some years will be the first economy in Central Pacific. Now, the first economy, Chile.
Okay.
This is a transition that leaves Peru in this moment.
Right. Okay.
The Peruvian state start to scholarship for our doctoral programs in medicine, in science, in biology.
Mhm.
So Peru different proposal in 21st century than 20th century.
Right. Okay. That sounds positive.
Global South, Indonesia, Brazil, Greece in economy, at the same time in university.
Mhm.
So I believe we'll live a new dialogue, new relationship within the global north, global south,
Okay.
between United Kingdom, England, and of course Peru. In this new relationship, new dialogue, we can find opportunity for institution.
Yeah. Absolutely. Yeah.
UCL public, San Mark is public. The public university has many challenges. Always budget,
Yes.
but we work for the community. We work for local communities.
Right.
So I'm sure the San Mark experience will be very important for your students and professor.
Mhm.
We have time.
Yes. Yeah.
We have time. We have the 25 years, the 21st century. In 10 years, Lima, capital of Peru, celebrate 500 years old.
Yes, I saw that. I did have a look at the web page. I thought we're celebrating 200. You've been longer.
In 20 some years, San Mark University celebrate 500 years old.
Mhm.
In this moment, we had a meeting with the University College London. Next month,
Okay.
will participate the director of the political science from University College London. The idea is connect the public university
Mhm.
in this transition, in
Okay.
this new dialogue between the global south and global north. We need this experience approach to help the people, to help the young, because the young, our student, will be the leaders, United Kingdom and Peru tomorrow. In this vision, I would like to start a proposal about the mode or agreement between institutions, between faculties, but it's difficult, yes. It's distance, it's different culture, okay. But London and Lima has a long common experience.
Yeah. Yeah, I think with agreements, it's really dependent on what you're interested in agreeing, because some things are way above me, so they have to be agreed at the sort of provost or vice provost level, not department level. Other things are more, at the faculty level, and then sometimes you know, it's departmental level, but that would tend to be more to do with, you know, maybe hosting internships or something, but larger would be linking, you know, to you know, vice provosts or something and getting them involved in the discussion. I mean, UCL likes to call itself London's global university, so they are always very keen on having strong international partners. So it's definitely worth something exploring.
Bien, amigos, amigas, ¿tienen preguntas, comentarios, por favor?
Good afternoon, teacher. First, I would like to congratulate your great presentation, but I would like, if you don't mind, to share with us your online for a future contact, please.
Sorry, I missed that. To share your
Email to contact with you.
Oh, my email.
Okay. Colegas, se compartió por el chat los websites respectivos. La universidad, el departamento, la facultad y el laboratorio de la profesora Carmal.
Muchas gracias.
Pueden consultar el chat, por favor. ¿Alguna consulta, alguna pregunta, algún comentario? Well, Claire, in our experience, first virtual connection, in the 1 month, 1 year, the professor visit Lima and share his or her experience in Lima in our seminar. We have some professors from Africa, Australia, yes, Europe. Yes, it takes time. But the idea is the virtual and physical. Could be summer, July, August, the next year. It's opportunity, I believe, that you can note sign mark and our research. Of course, for us to have a more connection with laboratory, your research.
Yeah, sounds interesting. Yes, yeah, I'm happy to discuss it further.
A professor from your university participating in our seminar before pandemic. Now she's director of the Institute the Advanced Study. She's from history, humanity.
Oh, right, okay, yeah. I don't know. I might not know it. I think there's 18,000 staff.
We have time to explore.
Yeah.
The idea is to work for the health the students and our local communities.
Yes, yeah. No, it sounds very good. Yeah.
Amigos, amigas, por favor, pueden prender su cámara para tomar una captura, para un recuerdo para Claire. Un momento. Por favor, si pueden prender su cámara.
Ya.
Uno,
1,
dos,
2,
tres.
3.
Momento.
Momento.
Sí,
I
uno,
can
dos.
understand that bit in Spanish.
Yes. Yeah. Well, Claire, I
I
hope that you can
hope
visit
that you
Lima.
can visit Lima.
You can
Yes, that would be
know
very nice.
the South Pacific,
South Pacific.
Mhm.
and of course,
Of
know
course, know
our
our
community.
community.
Our community is
Our community is
similar to London.
similar to London.
You can find
You
in
can
Sagnar
find in
people
Sagnar
can
people
speak
can
Quechua,
Quechua,
Taninca,
Taninca,
the original language in
language
South America,
South America.
and
Yes.
of course,
Of course,
with Union
with
Kingdom,
Union Kingdom,
we have a tradition that start
tradition
before our
before
independence.
our independence.
In the Peruvian
Peruvian
independence as a
as a
England experience.
England experience.
Right, okay.
So
Yeah.
our universities are publics.
Are publics.
At the same, we have the
At
common
the same,
experience
we have the common
about the
experience
difficult to
of
talk
the
to the
difficult to talk to
authorities, the central authorities.
Yes.
central authorities.
Right, okay.
Well, un gran saludo.
Un gran saludo.
Por tu intermedio, un gran saludo al señor decano
Saludo al señor decano
de
de
Ciencias Matemáticas,
matemáticas,
Matemáticas y Ciencias
matemáticas y
Físicas.
ciencias físicas.
Our
Nuestra
faculty,
our
the science faculty,
faculty
start in middle
start in middle
19th century.
19th century.
Okay.
The faculty of science
The faculty of science
in 20th century,
20th century,
chemistry, mathematics,
mathematics,
Mhm.
then physics.
then physics.
So,
So,
well, amigos,
well,
amigas,
amigos,
muchas gracias
amigas,
por su
muchas
presencia.
gracias por su presencia.
Cordialmente los invito.
Cordialmente los
Tenemos la
invito.
próxima sesión el 26 con la Universidad de Gante.
Universidad de Gante.
Este mes tenemos a la Universidad
A la
de
Universidad de
París-Saclay
París-Saclay.
y finalmente la
Y
Universidad
finalmente la Universidad
Federal de Río de Janeiro.
de Río de Janeiro.
Nos acompaña el director de Ingeniería Nuclear. Entonces, Claire, thank you.
So yeah, you're more than welcome.
I want to say something special for you.
Oh, right, okay.
I want to say thank you for everything.
Oh,
Was
thank you very
clear.
much.
Your exposition. Thank you so much.
Thank you. Thank you. That's kind of you.
Thank you. Bye-bye.
Hey, thank you for inviting me.
Gracias.
Thank you. Goodbye.
Thank you very much, teacher.
Thank you very
Goodbye.
much.
See you soon. Bye-bye.
Bye.
Bye-bye.
Thank you very much.
Thank you very much.